Hello and welcome back, everybody. Today in geometry, we will be discussing the second half of section 9.5, going into the homework now because we're no longer proving those theorems for the parallelograms, but rather going to apply it this time around. Okay, so there are two big things that we need to cover for this section. The first one is what is known as the midline theorem. That was something that I wanted to split into the second part because I just wanted to make it so that it's a little bit easier for you guys. In addition to that, there's also defining what is a trapezoid. That is something that we didn't do earlier, so we're going to go ahead and do that this time too. Okay, so here let's go ahead and dive into the big piece of it, which is the midline theorem. So the midline theorem says that, hey, if you have any triangle, the segment formed by the midpoints of any two sides is half the length of the third side and is parallel to it. So this one is actually very, very important because here in the picture, this is what it's saying. We have triangle ABC, which you can see in the picture. We're told that D is supposed to be the midpoint, just as E is supposed to be the midpoint. According to the midline theorem, then that means that if I create segment DE right here, that length is supposed to be half of the opposite side, which is BC. So that is to say DE is 1/2 of BC. Or you can say that DE times 2 is equal to BC. But in addition to that, we also have to prove that this is going to be parallel to this guy that's over here. So that's the midline theorem, and we're going to go ahead and prove that right now, just to get it out of the way. Okay, so now that we know what is it that we need to do, let me just go ahead and write this as a restate. Okay, so in triangle ABC, if D is the midpoint of AB and E is the midpoint of AC, then I need to prove that DE is 1/2 of BC, or like I said, 2 times DE is equal to BC, and also DE is parallel to BC, the opposite side. All right, so let's see if we can kind of use all of that stuff that we had about parallelograms to kind of help us out, because this technically came afterwards. So my guess is that there has to be a use. So first off, what I like to do is I'm going to go ahead and put in some marks according to what's given. We know that D is the midpoint of AB, so that means we know that this side right here, and let me go ahead and use a different color pen. We know that AD right here should be congruent to DB right here because of the definition of midpoint. In addition to that, we know that AE is going to be congruent to EC because, again, definition of midpoint. Now, let me get rid of a small little piece right here because this is what I need to show, which is parallel, so I can't put that quite there just yet. Let's see. Let me go ahead and fill this part in. And what I'll do is I'm going to go ahead and put in a parallel with a question mark next to it because that is what is it that I need to show. Okay, so there it is. All right, so to continue with the proof, here's what we're going to do. We're going to take DE and extend it beyond the point E. Okay, we're going to take DE and extend it to a certain length right here. So basically, I am going to use like the line postulate and point plot to extend upon it. So then that way, how far do I want to go? Well, I want to go out to some point we'll go ahead and call F, such that DE and EF are going to be congruent to each other. Okay, so here I am going to introduce point F on DE such that E is the midpoint of DF. Okay, so you can see that's going to be my creation in this case. All right, so if E is going to be my midpoint, then what's going to happen is, well, I guess we can kind of fill in a little bit more too. I can go ahead and technically create FC, which is over here. And if you notice now, we basically have two triangles that definitely look like they are congruent to each other. Now, since I created that point F to be a specific length, and that length is such that it's equal to EF is congruent to DF, then that means that these two guys over here are going to be congruent to each other. And so by vertical angle, then that means that these two are congruent to each other. And so now we can say that by SAS, triangle ADE will then be congruent to triangle CFE. Okay, so right there, we show that these two triangles are congruent to each other. And that's nice because if you notice earlier, we said that these two are congruent to each other because of the midpoint, because D is the midpoint. Well, according to corresponding part, AD right here should then be congruent to FC right here. So that tells me that we also have a congruency over here. So by transitivity, now we have FC is going to be congruent to DB over here. Okay. In addition to that, from earlier, we can also say that because of corresponding parts, these two angles right here, A and also F, oops, sorry, not angle F, my fault. It's going to be angle ECF over here. Those two are congruent to each other by corresponding parts. And the reason why I need that is, well, looking at those two angles, angle A and also angle ECF, you'll notice that FC is going to be a side of angle ECF, and just as AB is going to be a side of angle A. And those are more specifically alternate interior angles. So by alternate interior angles, now we can go ahead and say that those two sides on the opposite are going to be parallel to each other. Okay, so now we have this piece right here is going to be parallel to this piece. So let me just kind of write down as a recap as to what has happened so far. By SAS, these two triangles are congruent to each other. And then we can say by CPCTC, AD is equal to FC. And then by, let's see, transitivity, we can say now that DB is equal to FC as well, because from earlier, AD is equal to DB by definition of midpoint. Okay. And then what I just concluded earlier was that we're going to go ahead and use CPCTC one more time to say that angle A is congruent to angle ECF. Okay. And then from there, we can say by AIP that AB, the side, is going to be parallel to FC, the side. Well, as of right now, if you're wondering, okay, well, where's all of this going to get us? Right now, from what we have is that we say that this side is going to be congruent to this side. This side is also parallel to this side. And from the last part, the last thing that we did, if you remember, from the previous day, we looked at certain theorems about a parallelogram. There is one that we said is called Theorem Dave, which says that if you have a quadrilateral where the opposite sides are congruent and parallel to each other, then that means that you actually have a parallelogram then. So then now we can say by Theorem Dave, and I really should give it a better name, we can say that now we actually have quadrilateral D, F, C, and then B is a parallelogram. Okay, we can say that those two are parallelograms because, again, the opposite sides are congruent and the opposite sides are going to be parallel. Okay, and that right there is definitely going to help us conclude it now, because if you have a parallelogram, that tells me that DF or DE is going to be parallel to BC by the definition of parallelogram. In addition to that, how do we know that it's going to be half the length then? Okay, so how do we know that it's going to be half the length? Oh, here we go. We know that BC is going to be congruent to DF. Okay, we know that DC is going to be congruent to DF. If I know that E is the midpoint right here, then that means that this length right here should definitely be half of BC then. Okay. So then since we know that, so here, let me kind of write this down. So then BC is going to be equal to DF. Okay. By theorem, I think it was, we call it APO. Okay. Which says that if you have a quadrilateral, if you have a parallelogram, the pairs of opposite sides are going to be congruent to each other. And so if that's the case, then we can say that BE is going to be equal to 1/2 of DF then, because remember, we're told that E is supposed to be the midpoint then. Okay. All right, so that's the big one that's out of the way. We're going to see how we're going to use that in just a little bit. What I want to do now is introduce the definition of a trapezoid, okay? So a definition of trapezoid, and see how all this is going to be linked up. If you have a trapezoid, here is a picture of one that's on the right-hand side. You can see A, B, C, and D. Our formal definition of a trapezoid is the following. We can say that the quadrilateral ABCD is a trapezoid, and we denote it as the following. You draw a little small trapezoid, and then call it by the vertices ABCD. According to the definition, and so this is a formal definition here, a trapezoid means that only one pair of opposite sides will be parallel. So that is to say, in this picture, only one pair of opposite sides are parallel. So in this case, I'm looking at AB and DC over here. They are parallel to each other, whereas AD is not parallel to BC. Now, be very careful. This is different from when we define what is an isosceles triangle versus an equilateral triangle. Isosceles triangle says that at least two sides are congruent, so therefore an equilateral triangle is a subset of it. But in this case, we cannot do the same thing. A trapezoid is not a subset of a parallelogram because trapezoid says specifically only one pair of parallel sides, whereas parallelogram says two pairs of parallel sides. So what I want to do is I want to go ahead and think about what happens over here, right, with this midline theorem that we just proved. And, well, what happens if I apply it to the trapezoid? So here, once again, you can see that we have a trapezoid on the right-hand side, okay? You'll notice what I'm going to do is I'm going to go ahead and introduce point E and point F such that E and F are supposed to be the midpoint of their respective sides. So that means that EA is going to be congruent to to ED, and then we also have BF is going to be congruent to FE. Well, looking at this picture, we form something called EF over here. And by the way, there is a name for it. That is called the median of the trapezoid. Okay, so with all that's given over here, okay, given that we have a trapezoid ABCD, where AB is parallel to DC, E and F are supposed to be midpoint of AD and BC respectively. So we said that EF is supposed to be the median. What kind of conclusion I want to create? Well, it looks like EF, right, is going to be parallel to the two sides that are given, right? So here, maybe that is going to be one of my conclusions. I want to prove that EF is parallel to AB, and also EF is going to be parallel to DC. In addition to that, well, this one is not going to be as obvious, but EF is supposed to be the average of the two sides. Okay, EF is supposed to be the average of those two sides that it's parallel to. So that means EF is equal to 1/2 multiplied by AB plus DC. Okay. Now, how to connect it all? Well, maybe you can help me out with here. Okay. So the proof of it, maybe not as obvious, but if you can see it, that'll be great. What I'm going to do is maybe I can go ahead and introduce a diagonal, maybe like say AC over here. And if you notice what I created over there, AC, hey, let's go ahead and call this point, we'll go ahead and call X. Now my question is to you, well, maybe what we can do is apply the midline theorem and see how this works out, okay? So let's see here. If I create that, then we can say that XF is going to be half of AB. And then in addition to that, we can say that EX is going to be half of DC. And then by by addition property of equality, then we can add them all up. So here, let me just kind of write that out here. So by the midline theorem, okay, we can say that XF is equal to half of AB. And then we also can say that XE is equal to half of DC. And as we said, if we add them up, XF and XE, let's see, XF plus XE is equal to 1/2 of AB plus CD. And this guy right here, well, according to the segment addition postulate, that is the same thing as EF. So there it is. That's going to be our proof. And the first part, if you're wondering, well, how is it parallel to each one of these? Well, the midline theorem covers that also, because if you remember, midline theorem also says that this part right here is going to be parallel to this part right here, just as this right here is going to be parallel to this part right here. All right. Okay, so now let's go ahead and apply these theorems so then you can see how to actually work it into your homework. So in the first one right here, let's say that we're given a parallelogram PQRS. I'm also going to tell you that M is the midpoint of QR. And then finally, what I need to do is I would need to prove that MX is going to be 1/2 PQ. Okay, so let me go ahead and draw in all the stuff that we know. PQRS is supposed to be a parallelogram, so that means that we can draw this in there, we can draw this in there. We can go ahead and sneak this guy in there and sneak this guy in there. Okay, so by definition, that's why I can put all of those down. What I'd like to do is I'd like to prove that this guy right here, if I call it X, then this is going to be equal to 2X. So then that is going to be my question marks. Well, let's go ahead and start extracting information. Okay, now definitely from what I'm seeing in this picture as a strategy is that I want to use the midline theorem, because if you notice the conclusion, I want to prove that XM is going to be equal to half of PQ. Now, in order to use the midline theorem, I need to know that M is the midpoint, which is given to me. So great, that's one part. But then the other part is I need to somehow show that X over here is also going to be the midpoint. And I noticed that I shouldn't use X for both of these. So let me just go ahead and call this A over here. Oops, sorry. Let me go ahead and call this A over here. So then that way this is going to be 2A over here. Okay. So the question is, well, how do we show that X is going to be the midpoint? Now, the one information that we have not extracted yet is this guy over here, that that we have a quadrilateral. You'll notice that X definitely looks like it's going to lie on the diagonals of the parallelogram. And now that it comes to mind, there was a theorem, I think it was theorem Dave in this case, that says that for a parallelogram, the diagonals are going to bisect each other. So I think that actually might work out in this case. Okay. So let's see. Let me go ahead and put that over here. Oh, and actually, you know what? I just realized something too. Let's see. By theorem Dave. Ooh, I cheated for this one. This is not called theorem Dave. It was called theorem Citrus, if I remember correctly. So let me go ahead and change that over here, because we have a side and the sides are congruent and parallel. Yes, so that is actually theorem Citrus. Okay, and just to make sure that I was correct, right there, see, theorem Citrus. If you have a parallelogram, then one pair of opposite sides are going to be parallel and congruent. Yes, okay, sorry about that. I just had to kind of sneak that in there just to make sure that I don't make a mistake on this. But anyhow, let's see, going back to this, let's go ahead and write the proof then. Okay, so since we know that PQRS is a parallelogram, then by theorem Citrus, okay, we can say that SQ and peak R bisects each other. Okay. And then by the definition of midpoint, okay, X is the midpoint of PR. And right there, I think we have everything that we need, because now that we said that X is the midpoint, and M is supposed to be the midpoint, okay, by given, M is the midpoint of RQ, then we can now go ahead and use the midline theorem. Okay, using the midline theorem, we can say that XM is equal to 1/2 of PQ, and there you go. And that's going to be our proof. Okay, so nothing too difficult, hopefully. All right, now let's go ahead and look at the last one right here, which is going to be a little bit easier. I want you to do a little bit of algebra, right? I want you to solve for X knowing the following facts about the given trapezoid and its median. So here we have in display a trapezoid, and then we also have the median over there. So that's what's going to be our assumption. Well, according to the midline theorem for a trapezoid, if you remember from here, we said that the median is supposed to be half of the, the median is supposed to be parallel and also be equal to the average of the two opposite sides, or the two sides that is parallel to. So in our case, we can do something very quick then. We can say that 2x plus 4, which is supposed to be equal to the median, is equal to half of this guy and this guy right here added together because it's the average. So 2x plus 1 and then plus 3x plus 2. Okay, well, now it's just a matter of doing the algebra, which I'm hoping it should be okay for you guys. Multiply the 2 to the other side over here. So we get 4x plus 8, and that's going to be equal to, for the inside added together, that is 5x plus 3. Move the 4x over. Okay, so that gives me x plus 3 is equal to 8. And then now if I subtract 3, then that means that x is equal to 5. And there you go. And then we're done. All right, well, I think that should do it. Thank you so much for watching, and I will see you guys next time. Have a good one. Bye-bye.